This is your presenter Asloob Mudassar, and I am presenting slide number 11 of the course on laser physics. Question: how the net loss in photon flux is balanced by the net gain in one round trip in a laser cavity during the lasing process? Answer: let F is the photon flux of a plane wave at any location in a laser cavity. In one round trip of the plane waves, the photon flux becomes equal to F into R1 into R2, and then the square of 1 minus Li multiplied by e to the power 2 sigma 2 1, and within parenthesis we have n2 minus g2 over g1 times n1, and the parenthesis closed, and then multiplied by L, where L is the length of the cavity and capital Li is the cavity loss per pass. During the lasing process, the cavity loss must be compensated by the cavity gain, or in other words, flux at one location in the cavity must be equal to the flux after one round trip, which may be expressed mathematically as given in equation number 11.1. You see that above we have said that capital F is the flux at any point, and then after one round trip the flux is this, which is given in red, F into R1 into R2 and so on. So you see that these two must be the flux, these two must be equal to each other if the loss has been balanced. So the equation 11.1 is due to because the flux at one location in the cavity must be equal to the flux after one round trip, that is the loss has been balanced. So equation 11.1 is F is equal to F into R1 into R2, and the square root of 1 minus Li multiplied by exponential factor. This is known as the threshold condition, which can be expressed as. So you see that we can express the simplified version of equation 11.1 in equation 11.2, which is very straightforward. Here where Nc is equal to N2 minus G2 over G1 times N1 is regarded as the critical inversion required for the threshold condition to reach. A second expression for Nc in terms of the cavity parameter can be obtained from equation 11.2, which is given by. So this is Nc, which is equal to minus, and then in the numerator we have log of R1 into R2 plus 2 times log of 1 minus Li divided by 2 sigma 2 1 into L. So this is actually we have solved N2. Actually, if we solve this equation, that is the equation number 11.2, for the value of N2 minus G2 over G1 into times N1, if we keep this factor which we call as Nc on the left hand side and regard it as Nc, then the right hand side can be written as given in equation number 11.3. So population inversion required to initialize the stimulated emission must have a population in the level 2 as given. So you see that since Nc is equal to N2 minus G2 over G1 times N1, we can solve equation 11.3 for the value of N2, which is given as in equation number 11.4. So we have N2 is greater than equal to G2 over G1 times N1 minus log of R1 into R2 plus 2 times log of 1 minus Li divided by 2 into sigma 2 1 into L. So you see that this is what we have obtained, the value of N2, that is the population in the level 2 under some constraints as given by equation number 11.4. The pumping mechanism should be such that the population of the level 2 must satisfy the condition given in equation number 11.4. This condition will ensure compensation of cavity loss and sustainability of stimulated process, and thus that of the lasing process. So you see that equation 11.4 giving a constraint on the value of N2 is actually the condition under which the loss is compensated. So this is the end of slide number 11.